and this is my rocket. It is 45 centimeter in length and 5 centimeter in diameter, and its weight about 437 grams. This is the nose cone. It is a parabolic nose cone with a shape parameter of 0.7. A parabolic nose cone is a very efficient nose cone which reduces the drag and increases the altitude. Um, it, it has the shape parameter of 0.7. This nose cone is 12.5 centimeter in length and it has a base diameter of 5 centimeter. This nose cone is made up of fiberglass. Fiberglass is very strong material. It also has good thermal property and it is cost efficient material. Uh, this is my body tube. It is 30 centimeter in length and it has a diameter of 5 centimeter and a inner diameter of 4.8 centimeter. It is made up of craft phenolic, which is uh, a lightweight, strong and durable material usually used in building model rockets body tubes. Uh, this rocket maintains stability by this the set of three trapezoidal fins. Uh, this the dimension of these fins are the root chord of the fin is 4.2 centimeter and it has a height of 4.8 centimeter and has a sweep length of 5 centimeter. The fins are made up of balsa wood. Balsa wood is a very light wood which is usually used in building aircraft. These rockets reach an altitude of 1576 meters. It uses a motor of G50 IM6. It reaches a maximum velocity of 263 meters per second and a maximum acceleration of 152 meters per second square. It needs 15.9 seconds to reach its apogee and the total flight time is 338 seconds. It also has a very low ground hit velocity. It contains a payload which is 100 gram in weight and with a length of 16 centimeter and a diameter of 4.8 centimeter. This payload is located in the body tube. The payload will contain a flight computer and a battery and two ejection jars which will be like this. There will be a bulk head in front of the payload which will keep it steady. The After the rocket reaches its apogee, the flight computer will detect the apogee and the descent. As soon as it detects the descent, the ejection jars which are uh, situated in front of this bulkhead will blow up and it will push the nose cone front, and so the nose cone will eject out with the ejection of the parachute. This parachute will be connected to the centering rings here. Uh, there will be a shock cord connecting both of them. Because of the blowing of the nose cone, the payload will also eject out, so it will come in the contact with air. So, so the sensors which we have on our payload will give the necessary data the from that position. Uh, the actual bulkhead which we see here will have three holes, two for the ejection charge and one for the shock cord. Uh, Here I have a CAD model of it. This is the bulkhead with three holes on it. From the two ejection charge will be there, and by one hole the shock cord will connect the centering rings and the parachute. So the advantage of this technique will be that if we imagine that the same payload is always the payload is always uh, positioned in the nose cone. So the nose cone is a very small place for the payload. So the size of the payload is reduced. So sometimes by my first modules, I understand that I had a very greater mass. I can carry a very large mass on my rocket, but the thing which actually was happening was the it was the payload was not much bigger. Um, so the density of that payload was about 2.8 gram per meter cube. So it was like carrying, we can only carry a bar of aluminum. Aluminum has a density of 2.7. Even if we only carry aluminum, it would be less for the rocket. So if the weight differs, the location of CG differs, and the stability also differs. So the altitude is reduced because of it. So though the rocket could fly, it was not practically possible. Uh, by my first models, I was able to go at the altitude of 2,500 meters, but the thing was the payload was having a high capacity, but it was having a low volume. Uh, so so it defined what payload uh, you must have. So then I scaled my rockets, and I have this one with a greater size, and which is actually possible. We can fly. So I just wanted to show it has a stability of 0.6, about 0.6 caliber, and I made its stability such that it would be its average stability. Its average stability would be 0.8 caliber, which makes it stable, not overstable. So this rocket could be used for different purposes, for studying the atmosphere up there, and we can have a lot of data with which we want. So if even we can have compu- um, have a camera situated uh, in the payload. As it comes out, we can also give the ground scenario. So it has many uses as per we can use it. So thank you.